Hey everybody, it's Mrs. Dinkelman, and we're in Unit 10 where we're testing series for whether it converges or diverges. And the two tests we're talking about in this particular video are the telescoping series and the integral test. So a telescoping series is really just a specific kind of series, and what happens with it is it collapses on itself, kind of like an old school telescope that they would have had a long time ago, not like the ones we would use today that are just set up. So you'll see here with this particular thing, in example one, we have like a negative a half and a positive a half that would cancel each other out, and then a negative a third and a positive a third, and so on. And so we're just assuming that what's going to happen here is we're going to collapse all the terms. We're still left with a 1 at the beginning, and then the very last term in this one would be 1 over infinity, which would be 0. So we just get equals to 1 here. So the telescoping it's not really a test, it's just that you look at it and notice that it is telescoping. I'm going to real quick go to the assignment here and see if it's possible that I gave you one that wasn't. So it's possible that, and I think on number 5, as I'm looking at it, this one, what you probably need to do is do partial fractions so that you can write it in a way that looks like this. So if you want to just write yourself a little note there on number 5, try partial fractions and then see if it's telescoping after that, okay? And okay, the second test we're talking about is the integral test. And so if we have a function that's positive, continuous, and decreasing, so we don't want to talk about things that are below the axis. I'm thinking like an integral, I always think about area, which is why I have this wrap-up question here. So we don't want things below the axis because that could cause like negative infinity issues. What we're going to do is we're just going to take the antiderivative of the series, and we'll see whether that converges. And then if that converges, we'll say that our series converges. If that diverges, then we'll say our series diverges. I'm going to switch these to x's because that just makes more sense to my brain. So I think this is a natural log problem because the derivative of the denominator is 2x, which is really close to what's going on in the top. I just have to make an adjustment because the derivative of this would be 2x. I need to divide by 2 because there isn't one there. And then I'm just going to automatically say, oh, well, natural log of infinity, that's infinity. So this diverges, which means this guy diverges. This is also a really good time to talk about why that 1 over n, that p series, would diverge, because if we do the integral of 1 over x from 1 to infinity, we get that natural log thing again. And if we try other versions of this, we can kind of prove using the integral test why that p-series test works the way it does, if that's helpful for you to remember. Okay, so go ahead and get to the assignment, and you'll see hopefully some that are definitely in the form of telescoping. Actually, I'll do number 1 with you so that you can see what I mean by that. That our example was written out as telescoping and this one isn't. So what we would want to do is write it in expanded notation. So we'll start with n as 1. So if I plug a 1 in here, I'm going to get 1 over 2 minus 1, so that's going to be a 1. And then if I plug a 1 in here, I'm going to get 3 there. And next I'll plug in a 2, so 4 minus 1. And then 4 plus 1. And when n is 3, so 6 minus 1. And then 6 plus 1. Okay, so that's how you would write it in expanded notation before you determine what the final answer is going to be. A lot of times it's 1, you'll notice, but you just need to write those out in expanded notation to get there. All right, I'll let you get to it.